Good day. We are going to have the discussion of Gaussian elimination. In this discussion, we will develop a systematic procedure for solving system of linear equations. The procedure is based on the idea of performing certain operations on the rows of the augmented matrix for the system that simplifies it to a form uh, from which the solution of the system can be ascertained by inspection. Now, um, when we when considering methods for solving systems of linear equations, it is important to distinguish between large systems that must be solved by computer and small systems that can be solved by hand. For example, um, there are many applications that lead to linear systems in thousands or even millions of unknowns. Large numbers or large systems require special techniques to deal with issues of memory size, round of errors, solution time, and so on. Such techniques are studied in the field of numerical analysis and will only be touched on this discussion. However, um, almost all of the methods that are used for large systems are based on the ideas that we will discuss later. So the first one is the echelon forms. Okay, now in the previous examples that we had, okay, we solved the linear system in the unknowns x, y, and z by reducing the augmented matrix to the form of this one. Okay, now in this augmented matrix, we have the solution of x equals 1. Okay, so this is our x. So here we have x equals 1. This is our y. So you have y equals 2. And this is our z. So it means z equals 3. Okay, so this is becomes more evident. So in this example of the matrix uh, that is in the reduced row echelon form. Now, to be in this form, a matrix must have these properties. So these are the properties of the reduced row echelon form. Okay, so number one, if the row does not consist entirely of zeros, then the first non-zero number in the row is the one. We call this a leading one. Now, number two, if there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. Okay. Another, in any two successions or two successive rows that do not consist entirely of zeros, the leading one in the lower row occurs farther to the right than the leading one in the higher row. And the last one, each column that contains a leading one has zeros anywhere else in that column. So a matrix that has the first three properties is said to be a row echelon form. In other words, the matrix in reduced row echelon form is of necessity or necessary in row echelon form, but not conversely. Now, let's have this one. Okay, so this would be the examples of reduced row echelon form. And this would be the examples of the row echelon form, but not reduced row echelon form. Okay, so these are the illustrations. Okay, now, Suppose that the augmented matrix for a linear system in the unknowns uh, x sub 1, x sub 2, x sub 3, and x sub 4 has been reduced by elementary row operation to this one. So this matrix is reduced row echelon form and corresponds to the equation that we have uh, x sub 1 is equal to 3. Okay, so we have this one. And then this will be our x sub 2. X sub 2 is equal to negative 1. This is our x sub 3. So x sub 3 is equal to 0. And x sub 4, okay, is equal to 5. Thus, the system has a unique solution, namely x sub 1 is equal to 3, x sub 2 is equal to negative 1, x sub 3 is equal to 0, and x sub 4 is equal to 5. Okay, now, so we have here in each part, suppose that the augmented matrix for a linear system in the unknowns x, y, and z has been reduced by elementary row operations to the given reduced row echelon form. So solve the system. So let's say we have letter, the first one. Okay. Now I'll give you time to answer this one and try to, what do you call this one? Try to, uh, post your answer in the in call messages. I'll give you time to do that. Okay. So in this case, as we can see, the equation that corresponds to the last row of the augmented matrix is actually 0x plus 0y plus 0z is equal to 1. So the last portion, this one. Now, since this equation is not satisfied by any values of x, y, and z, then we can say that the system is inconsistent. So this is inconsistent because there's no such thing as 0x plus 0y plus 0z equals 1. Okay, now let's have the next example. So again, um, solve the system, the second one, and try to write your answer in the in-call messages. Okay, so in this equation, um, the equation that corresponds to the last row of the augmented matrix is actually 0x plus 0y plus 0z equals 0. Okay, so we can see here that these are all 0. So since these are all 0, this equation can be omitted since it imposes no restrictions on x, y, and z. In other words, the linear system corresponding to the augmented matrix would be you have x plus 3z equals negative 1. And you have the second row, y minus 4z equals 2. So since x and y correspond to the leading ones in the augmented matrix, we call these the leading variables. The remaining variables, in this case, which is letter z, uh, these are called uh, free variables. So solving the leading variables in terms of the free variables would be you could have uh, x equals negative 1 minus 3z. And you have y equals 2 plus 4z. So from these equations, we see that the free variable z can be treated as a parameter and assigned an arbitrary value, so which is t. So which then determines values for x and y. Thus, the solution can be represented by a parametric equation. So you could have x equals negative 1 minus 3t, y equals 2 plus 4t, and you have z equals t. So by substituting various values of t in these equations, we can obtain various solution of the system. For example, setting t is equal to 0, okay, which yields at x equals negative 1, y is equal to 2, and z is equal to 0. Now, if we are going to set the value of t as to 1, so we have now a solution set of uh, negative 4, 6, and 1. Okay, so let's have the next example. So again, try to write your answer in the in-call messages. Okay, so as we can see on the previous example, actually the second one, it is explained that we can omit the equations corresponding to the zero rows. So in this case, okay, the linear system associated with the augmented matrix consists of a single equation. So what is that equation? So we have um, x minus 5y plus 1 equals 4, from which we can see that the solution set in a plane in the solution set is a plane, okay, in three-dimensional space. Although one is a valid form of the solution set, there are many applications in which it is preferably or preferable to express the solution in a parametric form. We can convert one, okay, we can convert this equation, the x minus 5y plus 1 equals 4, to a parametric form by solving for the leading variable x in terms of the free variable y and z. So in other words, we can now have the equation, okay, x is equal to 4 plus 5y minus z. By the way, this is not 1, but this is z. Okay. Now, um, from this equation, x is equal to 4 plus 5y minus z, we see that the free variables can be assigned arbitrary values. Let's say y is equal to s, okay, y is equal to s, and t, okay, would be our c. Okay, so we can now determine the values of x. So the solution set can be expressed parametrically as you have y, not y, x is equal to 4 plus 5s minus t, where y is equal to s and z is equal to t. Okay, now we will usually denote parameters in the general solution by the letters R, S, T, but any letters that do not conflict with the names of the unknowns can be used. For systems with more than three unknowns, subscripted letters such as T sub 1, T sub 2, T sub 3, and so on are convenient. Now, in this uh, solution, y is equal to 4 plus 5s minus t, where y is equal to s, z is equal to t, uh, it is express the solution set of a linear system parametrically have some associated terminology. So, what would be that one? We could have, if the linear system has uh, infinitely many solutions, then a set of parametric equations from which all the solutions can be obtained by assigning numerical values to the parameters, which is called general solution of the system. Okay, so elimination method. So we have been seeing how easy it is to solve a system of linear equations once its augmented matrix is in a reduced raw echelon form. Now, we will have, we will now give a step-by-step elimination procedure that can be used to reduce any matrix to reduce raw echelon form. As we state each step in the procedure, uh, we illustrate or we are going to illustrate the idea by reducing the matrices or the matrix to reduce raw echelon form. So let's have this one example. You have 0, 0, negative 2, 0, 7, 12. The second row is 2, 4, negative 10, 6, 12, 28. And the third row would be 2, 4, negative 5, 6, negative 5, negative 1. So our first step in this case is, of course, locate the leftmost column that does not consist entirely of zeros. So our leftmost non-zero column would be this one. Okay, this would be our leftmost. Now, in this case, we have to interchange the top row with another row if necessary to bring the non-zero entry to the top of the column found in the first step. So in this case, we could have, okay, we can write this one as you have 2, 4, -10, 6, 12, 28, and then you have 0, 0, -2, 0, 7, 12, and then you have 2, 4, -5, 6, -5, -1. So this would be our matrix. Okay, now the first and the second row in the preceding matrix were interchanged. Okay, now uh, if the entry that is now at the top of the column found in our first step is, let's say, A, multiply the first row by uh, 1 over A in order to introduce a leading coefficient. So in this case, we have the first row of the preceding matrix will be multiplied by 1/2. So we have to multiply here by 1/2 so that we could have a leading coefficient here of 1. Okay, so we have now our matrix would be 1, 2, -5, 3, 6, 14. Then you have 0, 0, -2, 0, 7, 12. Now, in this case, um, we have 2. So we have here um, 2, 4, -5, 6, -5, -1. So this would be our new matrix. Okay. So our next target would be we're going to make this third row uh, to be here, this element here to be 0. So we can have this one, we can make this one 0 if we are going to multiply the first row with -2, then we have to add to the third row. So if we are going to add, to multiply this one by 2, -2 rather, and then add to the third row, okay, we will now have, okay, copy the first two row. You have 1, 2, -5, 3, 6, and 14. Then 0, 0, -2, 0, 7, 12. Now, multiply this one, the first row by -2, then add to the third row rather. So you have 0, 0, you have 5, you have um, 0, you have -17, and -29. So this would be our new matrix. Okay, so let's just copy the matrix, the newly formed matrix. So you have 1, 2, -5, 3, 6, 14. Then you have 0, 0, -2, 0, 7, 12. Then you have a 0, 0, 5, 0, -17, -29. So this would be our new matrix. Now, in this case, um, we have to cover the top row in the matrix and begin again with the first step. So applied to the submatrix that remains. So continue this way until the entire matrix is in a reduced echelon form. Okay, so as you can see here, we have this one, the leftmost, okay, non-zero column in the submatrix. So in this case, so to make this uh the, to make this column, okay, this one to be this number negative 2 to be 1, we have to multiply this second row by negative 1 half. So if we are going to multiply that one with negative 1 half, then we have the first row, you have the 1, 2, negative 5, 3, 6, 14. Then the second row will be multiplied by negative 1 half. So you have 0, 0, 1, 0, 7, negative 7 over 2, and you have negative 6. Then copy the third row. So you have 0, 0, 5, 0, 7, negative 17, negative 29. So this would be our new matrix. Now in this case, okay, so in this case, uh, as we can see here, below in this new matrix, below 1, okay, below this leading coefficient 1 in the second row is 5. So our target here is to make this 5 as 0. So this one, we're going to make that one as 0. So we can only make that one as 0 if we are going to multiply, okay, we have to multiply negative negative 5 to the first row of the submatrix, um, added to the second row of the submatrix to introduce the 0 below the leading 1. Now, to make this 5 here as 0, to make this one 0, we have to multiply negative 5 the second row, then add to the third row. So we have to multiply here negative 5. So we have to copy the first row. So you have 1, 2, negative 5, 3, 6, 14. Then let's copy the second row. You have the 0, 0, 1, 0, negative 7 over 2, and negative 6. Now we have to multiply negative 5 the second row, then add to the third row. So you have negative 5 times 0 is equal to 0 plus 0. That's 0. Here, 0. So negative 5 times 1 is negative 5 plus 1, plus 5 rather, is equal to 0. And then here, 0. Then here, negative 5 times negative 7 over 2, that's negative 30, that's positive 35 over 2, minus 17 is equal to 1 half. Then you have negative 5 times negative 6 equals 30, minus 29 is equal to 1. So this would be our, okay, new matrix. Okay, now let's try to copy that last matrix. So you have uh, 1, 2, negative 5, 3, 6, 14, then 0, 0, 1, 0, negative 7 over 2, negative 6, and you have 0, 0, 0, 0, 1 half, and 1. Okay. Now, in this case, let's go over to the leftmost non-zero column of the new matrix. So this one, as we can see here, it is 1 half. So what we are going to do, we have to multiply this one. To make this one 1, we have to multiply, okay, this one by 2. So we have to multiply that one by 2. So what we have, new matrix, you have 1, 2, negative 5, 3, 6, 14, 0, 0, 1, 0, negative 7 over 2, negative 6, and you have 0, 0, 0, 0, 1, 2. Okay, so the entire matrix is now in the in row echelon form. So to find the reduced row echelon form, we need the following step. Okay, now uh in this what we call this one, new matrix. Okay, with the last non-zero row and working upward, add suitable multiples of each row to the rows above to introduce the zeros above the leading one. Okay, so in this case, so in this case, we have to multiply the third row. Okay, the third row by negative by 7 over 2, and then add to the second column. So we have to multiply here 7 over 2. Okay, so you have copy the first row. You have the 0, the not 0, that should be 1. So you have 1, 2, negative 5, 3, 6, 14. Then copy the third row. So you have 0, 0, 0, 0, 1, 2. Then multiply the third row by 7 over 2, then add to the second row. So this is 0, 0, and this would be 1. This would be 0. This would be, of course, is this would become 0, and you have here 1. Okay, because this is uh 14, 14 over 2, that's 7. Okay, plus negative 6, that becomes 1. So this would be our new matrix. Okay, let's try to copy that one. So you have um 1, 2, negative 5, 3, 0, 2. Then you have 0, 0, 1, 0, 0, 1. Then you have 0, 0, 0, 0, 1, 2. Okay, now in this case, we have to let me correct first our that is not the matrix. This should be 6 and 14. Now our next is we have to uh this one. Okay, the we have the first row should be convert to what we call this one. This one must be 0. Okay, so we have to multiply negative 6 to the third row. Okay, negative 6 to the third row, then add to the first row. So in this case, we have to copy the second row. 0, 0, 1, 0, 0, 1. Then third row 0, 0, 0, 0. Uh, let me check. It should be uh, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 2. Okay. So we have to multiply negative 6 to the third row, then add to to the first row. So this is 1, 2, negative 5. This is 3. Okay. Then you have 0, and you have 2. Okay. In this case, above the negative above in the second row, above the leading one here is negative 5. So our target here should be, this would be 0. So in other words, we have to multiply 5 the second row, then we have to add it to the first row. So in this case, we have to copy the second row, 0 0 1 0 0 1, and then the third row, 0 0 0 0 1 2. Okay, so multiply 5 the second row plus 2 the first row. So this would be 1 2. This would be 5 times 1 is 5 times plus negative 5 is 0. Then you have 3, you have 0, then you have 7. So this last matrix is our reduced row echelon form. Okay, let's have another example. So we're going to use the Gauss-Jordan elimination. So solve by Gauss-Jordan elimination. You have x sub 1 plus 3x sub 2 minus 2x sub 3 plus 2x uh, sub 5 equals 0, and so on. Now in this case, we have to make the system, okay, transform it into augmented matrix. So for our augmented matrix, so we have uh, you have 1, 3, negative 2, 0, 2, 0, 1. 0, 0 rather. Then you have 2, 6, negative 5, negative 2, 4, negative 3, negative 1, 0, 0, 5, 10, 0, 15, and 5. Then you have 2, 6, 0, 8, 4, 18, and 6. So this would be our augmented matrix. Now, we have to uh, add negative, uh, we have to multiply negative 2 to the first row, then add it to the second and fourth row. Okay, so we have, uh, again, we have negative 2 multiplied to the first row, and then add to the second and fourth row. So you have here, so you have uh, 1, 3, negative 2, 0, 2, 0, 0. Then for the second row, you have uh, 0, take note, multiply negative 2 to the first row, then add it to the second. So you have 0, 0, negative 1, negative 2, 0, negative 3, negative 1. Then we have to copy the third row, 0, 0, 5, 10, 0, 15, 5. Then for the fourth row, again, multiply negative 2 to the first row. Then we have to add it to the fourth row. So you have um, 0, 0, 4, 8, 0, 18, and 6. So this would be our matrix. Now, in this case, um, as you can see, our second row is uh, lead you have here negative 1 in our second row. So the second row is negative 1. Okay. So we have to multiply that one by negative 1 to make it positive. So you have um, 1, 3, negative 2, 0, 2, 0, 0. Then you have 0, 0, 1, 2, 0, 3, 1. Then you have 0, 0, 5, 10, 0, 15, 5. Then you have 0, 0, 4, 8, 0, 18, 6. Okay. So let's try to copy that one. So you have um 1, 3, negative 2, 0, 2, 0, 0. Then you have 0, 0, 1, 2, 0, 3, 1. Then 0, 0, 5, 10, 0, 15, 5, 0, 0, 4, 8, 0, 18, 6. Okay, so okay, in this case, we have to uh, multiply negative 5 to the second row, okay, then add it to the third row, and you have uh, negative 4 times the new second row to the fourth row. Okay, again, we have to um, multiply negative 5 to the new second row, then add it to the third row, and negative 4 times the new second row, okay, then uh, add it to the fourth row. Okay, so you have, in this case, 1, 3, negative 2, 0, 2, 0, 0. Then you have um, 0, 0, 1, 2, 0, 3, 1. Then you have 0, 0, um, 0, 0, um, 0, 0, 0. And then the last one. So you have uh, negative 4 times the new second row, and then add it to the fourth. So which have 0, 0, 0, 0, 0, 6, 2. Okay. Now, in this case, we have to interchange the third and fourth. And then multiplying the third row to the resulting matrix by 1 6. Okay. So we have to multiply it by 1 6. So we have to interchange, then multiply to 1 6. So you have 1, 3, negative 2, 0, 2, 0, 0. Then 0, 0, 1, 2, 0, 3, 1. Then you have, in this case, the new fourth row is 0, 0, 0, 0, 0, 0, 0. This is 0. Then you have 0, 0, 0, 0, 0, 1, and 1/3. Okay. So you have uh, 1, 3, negative 2, 0, 2, 0, 0, then 0, 0, 1, 2, 0, 3, 1. Then you have 0, 0, 0, 0, 0, 1, 1/3. Then 0, 0, 0, 0, 0, 0, 0. So that would be our matrix. Now in this case, okay, this in this case you have the leading, okay, uh this completes the forward phase since there are zeros below the leading ones. Now in this case, adding negative, we have adding negative, what we call this one, negative 3 times the third row, then add it to the second row, and then you have uh, 2 times the second row of the resulting matrix, then add it to the first row, okay, to have a reduced row echelon form. Okay, so again, we have negative 3 times the third row, then add it to the second row, and then 2, okay, times the second row of the resulting matrix, then add it to the first row so that we could have the reduced row echelon form. So you have, in this case, you have 1, 3, 0, 4, 2, 0, 0. Okay. Then you have 0, 0, 1, 2, 0, 0, 0. Then you have 0, 0, 0, 0, 0, 1, 1/3. And then you have um, 0, 0, 0, 0, 0, 0, 0. Okay. So this would be uh, the uh, reduced raw echelon form. Okay. So in this case, we could see here that the corresponding system of equation would be um, x sub 1 plus 3x sub 2 plus 4x sub 4 plus 2x sub 5 equals 0. Then you have x sub 3 plus 2x sub 4 equals 0. And your x sub 6 equals 1/3. Okay, so note that in constructing the linear system in 3, we ignore the row of zeros uh, in the corresponding augmented matrix. Okay, so solving for the leading variables, we can obtain uh, x equals negative uh, x equals negative 3x sub 2 minus 4x sub 4 minus 2x sub 5. And then x sub 3 equals negative 2x sub 4 and x sub 6 equals 1/3. Now, we can express general solution of the system parametrically by assigning free variables x sub 2, x sub 4, and x sub 5 by arbitrary values, let's say r, s, and t respectively. So that yields with x sub 1 equals negative 3s minus 4, negative 3r minus 4s minus 2t. X sub 2 equals r. X sub 3 equals negative 2s. X sub 4 equals S, x sub 5 equals t, and x sub 6 equals um, one third. Okay. Okay. Free variable in homogeneous linear system. Now, there are two important points, okay, about solving homogeneous linear system. The first one, um, we could have elementary row operations do not alter columns of zeros in a matrix. So the reduced row echelon form of the augmented matrix is a homogeneous linear system, has a final column of zeros. This implies that the linear system corresponding to the reduced row echelon form is homogeneous, just like the original system. Then the second one is the when we constructed the homogeneous linear system corresponding to the augmented matrix, we ignore the row of zeros because the corresponding equation would be zeros, like uh, 0 x sub 1 plus 0 x sub 2 plus 0 x sub 3 plus 0 x sub 4 plus 0 x sub 5 plus 0 x sub 6 equals 0. Okay, this does not impose any conditions on the unknowns. Therefore, depending on whether or not the reduced row echelon form of the augmented matrix for a homogeneous linear system has any rows of zeros, the linear system corresponding to that reduced row echelon form will either have the same number of equations as the original system, or it will have fewer. Now, consider a general homogeneous linear system with n unknowns, and suppose that the reduced row echelon form of the augmented matrix has r non-zero rows. Since each non-zero row, okay, has a leading one, and since each leading one corresponds to a leading variable, the homogeneous system corresponding to the reduced row echelon form of the augmented matrix must have r leading variables and n minus r free variables. Okay. Therefore, this system is in the form of this one. So this one. Okay. Where in each equation, the expression summation of the parentheses denotes a sum that involves the free variables. So in this case, we can now have a theorem. Okay. So this one, theorem 1.2.1, free variable theorem for homogeneous system. If the homogeneous linear system has n unknowns, and if the reduced row echelon form of each augmented matrix has r non-zero rows, then the system has n minus r free variable. Okay. Next, you have the theorem 1.2.2. Okay. So a homogeneous linear system with more unknowns than equations has infinitely many solutions. So that would be our theorem. Okay. So in retrospect, we could have anticipated that the homogeneous system would have infinitely many solutions. Okay, if uh, the homogeneous systems with more unknowns than the equation. Okay, so let's have the Gaussian elimination and back substitution. So for small linear systems that are solved by hand, Gauss-Jordan elimination, or also known as reduction to reduce raw echelon form, is a good procedure to use. However, for large linear systems that requires a computer solution, it is generally more efficient to use uh, Gaussian elimination, which is the reduction to raw echelon form, followed by a technique known as uh, back substitution to complete the process of solving the system. So let's have this example. Okay, so for the computation of this example, okay, a raw echelon form is raw echelon form of the augmented matrix is given. Now try to uh what to call this one? We are going to solve this one. So in this case, we could have what to call this one? Now to solve the corresponding system of equation, we have um x sub 1 plus 3x sub 2 minus 2x sub 3 plus 2x sub 5 equals 0. Then you have x sub 3 plus 2x sub 4 plus uh, 3x sub 6 equals 1. And you have x sub 6 equals 1/3. Now, we can have uh, get the leading variables in terms of the free variables. So we have here x sub 1 equals negative 3x sub 2 plus 2x sub 3 minus 2x sub 5. Then x sub 3 equals 1 minus 2x sub 4 minus 3x sub 6. And x sub 6 equals 1/3. Okay. Now, beginning with the bottom equation and working upward, successively substitute each equation into all the equation above it. So substituting x sub 6, which is equal to 1/3, to the second equation, this yields um, an equation of uh, x sub 1 equals negative 3x sub 2 plus 2x sub 3 minus 2x sub 5. Then x sub 3 equals negative 2 x sub 4. And of course, our x sub 6 would be 1/3. Okay. Now, substituting x sub 3 by negative 2 x sub 4 in the previous presentation, then you could have uh, x sub 1 equals negative 3x sub 2 minus 4x sub 4 minus 2x sub 5. Then x sub 3 equals negative 2x sub 4 and x sub 6 equals 1/3. Then for the final step, we have to assign arbitrary values to the free variables. Okay. Then uh, if we are now going to assign x sub 2, x sub 4, and x sub 5, the arbitrary values are s and t respectively. The general solution is given by the formulas x sub 1 equals negative 3r minus 4s minus 2t, x sub 2 equals r, x sub 3 equals negative 2s, x sub 4 equals S, then x sub 5 equals t, and uh, you have x sub 6 equals 1/3. Okay. Okay. Let's have this one. Suppose that the matrices below are augmented matrices for linear systems in the unknowns x sub 1, x sub 2, x sub 3, and x sub 4. These matrices are all in raw echelon form, but not reduced raw echelon form. Okay. Discuss the existence and uniqueness of the solution to the corresponding linear system. So let's have this one. You have 1, negative 3, 7, 2, 5, 0, 1, 2, negative 4, 1, 0, 0, 1, 6, 9, and 0, 0, 0, 0, 1. Okay. As we can see here, the the last row correspond to the equation uh, 0x sub 1 plus 0x sub 2 plus 0x sub 3 plus 0x sub 4 equals 1, which is indicating or uh, it would be evident that the system is inconsistent. So this is inconsistent because of this row. So inconsistent. Okay. Next. So this one. So in this, as we can see on the presentation, the last row correspond to the equation 0x sub 1 plus 0x sub 2 plus 0x sub 3 plus 0x sub 4 equals 0, which has no effect on the solution set. In the remaining three equations, the variables x sub 1, x sub 2, and x sub 3 corresponds to the leading ones, and hence are leading variables. The variable x sub 4 is a free variable. With a little algebra, the leading variables can be expressed in terms of the free variable, and the free variable can be assigned an arbitrary value. Therefore, the system must have infinitely many solutions. Take note that the number of equations is less than the number of unknowns. Okay. Then we have this one. Now, as you can see, the last row corresponds to the equation x equals 4, which gives us a numerical value for x of 4. Now, we can substitute this value into the third equation. So you have x sub 3 plus 6x sub 4 equals 9. Now, if we are going to substitute x sub 0 equals 4, we obtain, in this case, x sub 3 equals 9. You should now be able to see if we continue this process and substitute the unknown values for x sub 3 and x sub 4 into the equation corresponding to the second row, we will obtain a unique numerical value for x sub 2. And if finally we substitute the known values of x sub 4, x sub 3, and x sub 2 into the uh, equation corresponding to the first row, we will produce a unique numerical value for x sub 1. Therefore, the system has a unique solution. So, uh, it has a unique solution. Okay. So, that ends the presentation.